So we all know the need for the optical fiber. Now Airtel has rolled out the Extreme Fiber, the broadband service. So why everyone is trying to provide the optical fiber service? So we need to understand this. Okay. So optical fiber provides the fastest way of communication, and not only in terms of speed, but also in terms of the amount of information that we can transmit across the optical fiber. So optical fiber you can think is like a tube, a very tiny tube. How tiny? You can imagine it's thinner than the strand of a hair, and generally it is put into bundles of lakhs of optical fiber into one bundle, and that bundle is converted into like a cable, and through that cable we transmit the information, because information is at the end it's simply 0101. But how we transmit 0 and 1? Because it's a number. So of course we don't transmit 0 and 1. What we do is, for every 0 and every 1, we create a signal. It may be a voltage signal or current signal, and based on the signal we do something called amplitude modulation, or we also have the frequency modulation. So we use some modulation technique, and using that technique we create a signal which can be transmitted as a, you can say, light. So light is a normal wave, like light is electromagnetic wave, but we can further modify the way light oscillates. And because light moves fastest, so by sending the light through a cable, and we know that the entire earth is almost at finite length, and light is having the tremendous velocity. So any communication even across the earth, let's say if I take the farthest point on the earth, so what is the farthest point on earth? So I can say the farthest point will be if you make a one complete round around the equator. Okay. So let's say we have a like a fiber communication going from here and traveling all the way through, and reaching this end, which is the farthest point. So we can say the maximum distance is 2 pi r. So what is the like a worst case scenario of time? Like how much time it would take to reach the light? So I can say 2 pi radius upon the speed of light. Let's call it c. It could be more than that, because we don't have the regular cable moving in a straight line. It is moving across the cities and across the ports and sea and all. And if I estimate this rough time, this is 6.4 10 power 6, and it is 3 into 10 power. So roughly 2.213. Okay. And minus 2, and this is roughly like 14 something, 12, 13. So you can see it's taking, I mean, too much time. It is taking roughly 130 milliseconds, which is actually too much time. It's not a small time. So on a scale of computing, this time is actually a big time actually. So our communication won't be very fast. You can say it is although fraction of second. So to communicate across Earth, the worst case scenario we can assume is that it will take this much time. So to reduce time, we have multiple data centers, multiple servers across the world, which is spread. And the whole idea is to reduce the transit time of the information. So the world of computing occurs at a speed of light, and therefore we must manage things which may be slow enough at that speed, but still fast enough for the human perception. So for us, 1 second is too much time, because our brain is now like uh, you can say too much active to understand roughly 0.1 second and more than that. So when you play a video game, a lot of things changes quickly on the screen, and all those changes must be brought in an interval less than the human perception level, which means we must accomplish all those transition, all those computing in the time less than 0.1 second. If I can achieve the less than 0.1 second, then probably you will see that it's a real thing, like it's a live event happening in front of you. But reality is nothing happens on a live, I mean, scale. Everything takes its own time, just because the computing power is such that for you those calculations occur very fast within a fraction of a second, and then you end up seeing those things. Okay, to make things happen very fast, we have to be very careful about the kind of language which we use, the kind of processing that we undergo through, and various other technology. So you can say this all thing, you can say the entire world of communication, whether we have the cloud computing, we have data center, we have so many things. Now you're playing the online gaming stuff, you have Discord servers. All these are possible because of the speed of light. Okay. Now we couldn't have achieved anything without light. So you imagine that how powerful is light and how important is the light. And it is the light which is putting some constraint on communication. So our communication speed is confined due to light. So that is why, like now we are trying to move from the conventional binary system to the or from the regular computing towards the quantum computing, which can uh, use a different kind of the data called qubits, and that will have more information in a lesser number of bits. And that is how we can increase the quantum speed, I mean the transaction speed of information. And once the speed will increase, we can move from 5G to maybe 7G or 8G or 10G. So it will be the revolution. It is still in the stage in which it is not practical to put into place because of the temperature constraint and many more things. The world of quantum is so you can say subtle, or you can say sensitive, that it requires a temperature close to sub-zero temperature, the absolute zero temperature, where the quantum computing can take place. At high temperature, it cannot be taking place, and therefore we need to create a different kind of data center where all this calculation will occur. Anyway, that's the future, and you may be the one to witness that future after 50 years, 60 years, something, or it may come on. Anyway, so that is not the idea. The idea is optical fiber is actually meant for communication, and it uses a simple principle of total internal reflection. So that's a very simple thing. And communication is always in terms of light. So what we do is we modify light. The light undergoes some sort of modulation. We can call it amplitude modulation. We can call it frequency modulation. We can call it phase modulation. There are three types of modulation, and or you can say phase pulse modulation. And using one of the modulation technique, we transmit it across the optical fiber. So what optical fiber is? It's a very fine thin strand. I mean, it is so thin that I cannot draw. In this thin strand, you may have hundreds of optical fiber. This is so large. Imagine. I'm saying this is a thicker one actually. Okay, so you don't see optical fiber. You see always a collection of optical fiber because optical fibers are very very thin. Okay. So now how we achieve this? Let me draw the internal structure. So every optical fiber will have two main layer. Every optical fiber will have two main layer. And these layers are like two concentric layers, so they have same center. You can make it any shape. The inner layer we call the core, and the outer layer is called clad. This is the outer layer which is clad, and the core and the clad differ in terms of the refractive index. So the only difference is the core will have, let's say, refractive index NO, clad will have N2. The actual transmission will happen. So the light will travel through the core, okay, like this. So the traveling of light will occur through the core, and therefore the light must not enter this clad, and therefore it must suffer the TIR. And therefore, to suffer TIR, the condition is simple. For TIR to take place here, the refractive index of N2 must be less than N1. Because
Yes,
the
sir.
TIR only happens when you go from the denser to rarer medium.
Rarer. Yes, sir.
So clad is bound to be rarer compared to the core. Okay. So the first thing you need to remember is the clad part is always rarer compared to the core. But the difference is not much. It is, if you talk about the difference, practically it is kept in the third place of decimal. So if I say this is 1.51, maybe I can keep it second place, then it is like 1.50. So the difference only occur at that second or third place of decimal, and that is sufficient. Okay, that is sufficient. Why? Because the dimension is so small that light will anyway enter at almost grazing incidence, right? So if I make a very thin tube, then light cannot enter like the light will have very less scope actually, so it will enter like this. So it is very large angle, so we don't need much of the difference to make this TIR. So generally the difference is very small. Okay. The idea is that the clad, why we introduce clad, so that it is easy to suffer the TIR. Okay. And again, the question is why we need to use clad. I mean, if it is air, it will have even better chance of TIR. The answer is we need to protect the information. So any leakage of light is dangerous. So for you, it will leak, but in many ways, the leakage will reduce the intensity, or you can say the power of the transmission. So energy is important. Energy means like attenuation in terms of communication system. We call attenuation of signal. The signal will become weak, and a weak signal is difficult to detect. That's a problem. So we do not want it to be weaker while getting transmitted. So the leakage is something that we are very much prone to. We don't want at all there should be any leakage. We make sure that there is zero leakage of signal. And the zero leakage is in terms of energy, you can say zero energy of a signal, which means no light should escape the core or the clad. So we need clad, and this is not just clad. I mean, after this, you will have some protective layer, which is again physical layers, which is not part of the light. So this is just to protect the optical fiber from bending and all. So it provides the sufficient flexibility, and you collect a bundle of such optical fiber, and the bundle is again put into a cable form. So we have infinite bundles, and this entire bundle is in a cable. So one cable may contains maybe lakhs of optical fiber, and then such bundles are further bundled into a thick cable. So you can imagine it is like more than like I don't know how many, but it may go to crores of optical fiber is made into a single cable, and that single cable is connected to the world biggest servers which is mostly run by the Microsoft, Google, Apple, IBM, and few more. So they control almost the entire world communication. Communication is not wireless. Communication is always physical. So every information that you share across the internet is actually physically stored in those servers, and these servers are made in a remotest possible area so that even during the case of World War, I mean, the data should not be destroyed. So they have bunkers kind of servers. So IBM has made the world biggest bunkers, and most of the server of IBM is inside the earth, so that if there is a comet attack, if there is some world war nuclear attack, those information can be saved, because we cannot recreate those information in one fine day. So the today's technology is depending on the technology that we develop over the years, which is like over the 60, 70 years, we develop everything, and then we kept everything together. And now the technology is using the pre-stored information to create something new. Okay. So our present technology is actually dependent on everything that we created almost 60, 70 years back. From that time till this time, we have been creating things. Everything is stored physically, and you share the information which gets transmitted from those location called servers to the some localized server. From localized server, it is transmitted to the different cities, different countries, and all those transmission is physical. When that physical information comes to your modem through the connected wiring, then you use a small scale information channel called Wi-Fi, or the LAN system, which is a localized communicating system, through which you further retransmit to the various locations. And then Wi-Fi will have the router modem, the laptop will have the similar technology. So everything is electromagnetic wave. So they transmit those EM wave, which you capture and you decode the meaning of it. So that's how the Wi-Fi works. So you may think that it's wireless, but the thing is, the end point till the information reaches your end destination, it is almost a wired communication. It is not wireless. Now we can, of course, do the wireless transmission up to some distance, but that will not be in bulk. That is going to be very expensive. Okay. So the world is using internet, which is consuming infinite amount of energy and you can say bandwidth. So the physical transmission is the fastest way of doing it. If you want to do the sky wave communication, the problem is you have to send all the data first into sky, and then satellite will capture all those data, then satellite will re-throw back to the earth. But if I if we do the communication that way, it is going to be very difficult in terms of speed, because it will take time to reach the outer space. Then there's a delay in processing by the satellite. It will retransmit, will take again some time, and then we cannot achieve the task. So of course, that is being done for the dedicated NASA server, which takes care of all the space satellite, its information, data sharing, the cloud information, the weather information, and that is how using those data we do the weather forecast and so many other things. All those forecasts are very important, which is done by the NASA, because based on the forecast, you predict the rain, which in turn affect the agriculture. You predict the storm, which in turn saves the life of a passenger, because the plane is moving through the clouds, and so they know that this is a region of storm, and we should not go from that region. So all those things are there, of course. Okay, anyway, so optical fiber is anyway, it's a again a topic of interest from communication point of view also, and from interest of the ray optics chapter. Okay. So after core and clad, we have many you can say uh, protective layers. And so on. Okay, so let me do a simplified view of optical fiber. So this is the cross-sectional view, or maybe the longitudinal cross-sectional view of the optical fiber. So basically cylindrical. You can extend as much as you wish. And let me do this. So I'm doing the core part really thick, and the clad part a thin layer, and the rest is covered or insulated, so nothing can enter from this side. This is insulated part. So in BTech, if you undergo the what we call electronics and communication branch, then you will study a lot about the optical fiber and some more detailed mathematical things will come across. Now, because I am electronics engineer, so I can give you all the details with ease. It's very easy. So we have, this is called the axis. Again, these are only for the purpose of demonstration. We know that in reality, it is going to be very, very thin, right? Give some other color. Okay. So now, as I discussed, this is N1, this is N2, this is core, and this is clad. So now we have something called angle of incidence. So the signal is incident like this. Okay. And this is called the angle of incidence. Let's call it alpha. Now, if I try to maintain the alpha, then in how many directions we can have for the signal to enter? So it is infinite direction. And all those infinite directions will make a cone, right?
Yes.
So technically, this cone decides this is the cone which decides like all the signal entering this cone will get transmitted across the fiber. Now, alpha is something very, very interesting. That can we transmit every signal across the optical fiber? Or do we have some restriction on alpha? That is the question. And the answer is yes. There is a restriction on alpha. Every alpha will not make sure that it will undergo TIR. Let's see why. So first of all, you enter, let's say, from a medium. So I'm not going to make it one specific case. So what I'll do is I'll make it a general case. So this is also medium. You're entering from medium. Maybe the signal is entering from water and something. Okay. Something lighter. This is lighter.
So the rays like entering at alpha from.
Yeah, tell me.
So the rays entering
Yeah.
the optical fiber at alpha.
Yeah. Anything from 0 to alpha, not only alpha. Alpha is the last, the maximum angle that we are supposed to take. Okay, I'll just tell you why. Just wait a moment. Now, the thing is, imagine any ray entering at angle alpha. You can understand this is a normal. Do you realize this? This is normal because the medium will change along this line, correct? So when you enter this optical fiber in the core part at some angle alpha, and I'm assuming that N1 is more than the mu medium. So we'll assume that core is more than the medium through which you are entering. Okay. So the first entry will be from the rarer to denser medium. Yes or no? The first entry is, or the
Rarer to-
first refraction is from rarer to denser. Correct. And because the first entry is from rarer to denser, what do you expect? Will there be any TIR? Yes or no?
So no.
Of course, there's no question of TIR. So this is just a question of refraction. So what will happen? Light will reflect. And what do you expect? Light will bend towards the normal? Yes or no?
Yes.
So the only thing I can expect is the light will bend towards the normal. So now here is the biggest question. Now it will bend towards the normal. It will have some angle theta. And now this is the normal. If you draw the normal here, this is the normal. And this normal is from core to clad. Understood? And therefore, for these two layers, this is the angle of incidence. Do you realize this?
Yes.
And this angle is having value 90 minus theta. Correct? Now,
Yes,
what
sir.
is the condition for TIR? We know the condition for TIR.
Theta should be greater than theta, sir.
The angle of incidence should be greater than certain critical angle. And the critical angle for these two layers, we can define easily. So sine of critical will be how much? N2 by N1.
Yes, sir.
Correct? Because we are defining for the core and clad. So we have to make sure that at this location, the TIR should take place, and therefore the light can keep on moving inside the core. So this is what we are trying to achieve. Understood? This is our target. Now, when the angle of incidence will be like exceeding the critical, so bigger the angle, easier the TIR is easy, isn't it? Like for this part, as this angle will grow in value, the TIR will be easier.
Yes.
So we want this angle to be as big as possible. Correct?
Yes.
And this angle to be as big as possible, then it is easier. But if this will become smaller and smaller and smaller, a time will come when this angle will become less than critical. In that case, no TIR will take place. Yes or no? So
Yes.
bigger value is like appreciated because bigger value means easy TIR. But when it becomes smaller, it is risky. Isn't it? Now
Yes.
try to understand. Alpha and this angle, let's call this as beta. Alpha is and beta is. How alpha and beta are related in a way?
Nu m sine beta equals n1 sine theta.
Mu m sine alpha is n1 sine theta.
Sine beta.
Sine theta. The first
Theta.
refraction is this theta, no? The first refraction is here. And there so we have to confirm the TIR. And beta must be more than critical for TIR. The worst case scenario is roughly taking equal, right? It will graze. But we don't want grazing, we want more than only. Is this clear?
Yes.
So beta should be more than theta c, but beta is 90 minus theta. So it turns out with theta must be less than 90 minus theta c. So there is a restriction that theta should not be big enough. It must be less than this value. But we know that as alpha will increase, theta will increase. Correct? As
Yeah.
alpha will increase, logically theta will increase. But if theta will increase, this is a danger. We want theta to be less than this value. So do we really want theta to increase for all values? No. And therefore, you can think the reverse way. First of all, the beta is having finite value. I mean, there is a range for which the TIR is possible, which in turn put a restriction on alpha also, isn't it? So can we
Yes.
keep on increasing the alpha?
No, sir.
If we keep on increasing the alpha, the theta will increase. If theta will increase, then 90 minus theta will decrease. So the beta will decrease, and if beta will decrease, it may fall below the critical, which means no TIR will take place. So the alpha is restricted. We are going to allow every signal to go through the optical fiber if the angle of incidence of that signal is anywhere from 0 to alpha, isn't it?
Yes.
So we are trying to find the alpha max. What is the maximum possible value of alpha that we can allow to get transmitted throughout the optical fiber? It's very simple. How to proceed any question of TIR? So you have to first look at the layer at which TIR is going to take place, and at that layer, you simply write this condition. That's always the starting point. After that, you go to the geometry part. So you will always have a right angle triangle. You can always see such kind of triangle. And then you can relate the relation. And then once you get this relation, once you are here, now you can go back to the next refraction, law of refraction from the outer medium to the core. So it's a reverse process. We don't start from here. We start from this condition. This is the first step. From here, we get the second step. And then to eliminate, we are going to use this third step. Okay. So let's do this. So we can see clearly what is 3 implies. What is sin theta? Sin theta is mu medium sin alpha upon n1, correct? And 2 implies, what is 2 giving you answer? Theta is less than 90 minus theta c. And then you do the same thing, you trick sin theta equals to less than, because sin is increasing function. So if you put sin both sides, the inequality remains same, right? If you take cosine, then it will reverse because it's a decreasing function, correct? And now because we got sin theta relation,
Yes.
I can substitute from here, which will give you the mu m sin alpha by n1 is less than cos theta c. And now we are done. So we are getting mu m sin theta, sin alpha upon n1 less than equals to cos theta c. So sin alpha is less than n1 by mu medium. And you can see this is putting the constant that alpha must be less than sin inverse of n1 by mu medium cos of sin inverse of n2 by n1. This looks really bad. This is a way of writing. In Trigo, you know how to write. And now you can see everything is in terms of what we need. So alpha max, which you can write is, you can see alpha must be less than this. For TIR, there is a restriction on alpha. So alpha max we can write as sin inverse. So generally they will ask you the inequality. Is this clear?
Yes, sir.
There are many ways in which
Yes, sir.
the answers will be given in the question and the way you can interpret. So we can also write from here directly. Mu medium sin alpha and cos theta c you can write as under root of 1 minus, and therefore this we can write as n2 by n1 whole square. And now again, this is a much more simpler way of writing. So alpha max, or simply alpha will be less than sine inverse of this mathematical term. So if you have already studied the ITF, you know how to manipulate all this, right? Have you done the ITF? Inverse?
So not.
No, sir,
Okay.
not yet.
No problem. So you can see again, there's a restriction. Alpha max is only this much, right? Okay, so you will study about all this ITF later on. So these are two possible ways in which you can express the answer. And now we'll come back to it. Which means if I send the signal at alpha more than alpha max, then many signal will transmit, but many will leak also. And that is what we don't want. So there is always a restriction that up to what angle we can achieve this transmission. And therefore, we define every optical fiber will have its well-defined. Every optical fiber will have its well-defined numerical aperture. So what is numerical aperture? So technically it is defined as sine of alpha max. So sine of alpha max is called numerical aperture, and it will decide that up to this angle, the transmission will suffer TIR and will get through the optical fiber. And anything more than that will get eliminated or will get leak out and something like this. So there was a question in JEE Advanced which was asked in 2016 or 15, I think, in which they defined the numerical aperture differently. So I mean, of course, the numerical aperture you may come across in a different way. It was comprehension question, and they defined the numerical aperture by multiplying with the mu of the medium. So in general, it is, I think, mu m sine alpha max. This is called the numerical aperture. This is for air, like when the mu medium is 1, like air. So in general, this is how we define the numerical aperture, and this aperture will decide that up to what angle the transmission will suffer the TIR and will propagate across the length of the optical fiber. So in JEE Advanced, they asked like two questions, that there are two optical fiber connected in series. So let's say because of some reason, the length of the fiber ended and then you join the other end. And for your information, it is very, very difficult to join two optical fiber. Because the gap should be non-zero. I mean, sorry, must be zero. The gap must be zero. We cannot afford slightest gap between the two joining. So it is done under a very special device in which the optical fibers are like kind of put within some other kind of, I mean, of course, it's a very complex device. And because if you join two optical fiber, you will have different numerical aperture. because let's say in the market it is not available exactly of same refractive index. So every manufacturer cannot create the same, right? So for some reason, if I have to purchase from two different manufacturers, we can expect the difference of N1 of this and N1 of this. Correct. So there is always a chance that N1 and N2 will have some N1, N2, and sorry, N1, N1 dash and N2, N2 dash will have some differences. And because of these differences, both will offer you different numerical aperture. So if I want to put this into series, then the numerical aperture which will transmit across both will be which one? So for that, let's say if I say if NA1 is more than NA2, let's say NA1 is offering you bigger, larger angle of transmission, but NA2 is offering you a small angle of transmission. So the net transmission, which transmission will be allowed across the combination?
NA2.
Correct. Only the smaller will dictate the final transmission, right? Okay. So let's say if there's a building to enter and there's a big lobby, you can enter it. But then there is a flat with a small entrance. So what will finally transmit through both will depend on the smaller opening or the smaller aperture, right? So the bigger aperture will not dictate the final transmission, only the smaller. Let's say from here truck can enter, but from here only bike can enter. So what will go through entirely? Bike or truck?
Bike.
Common sense, right? So similarly, if the first fiber is offering you Na1 and the second is offering you Na2, then what will eventually transmit across both? The one which is smaller, right? Understood?
Yes.
So they will ask you what is the numerical aperture of system. So because it is in the series combination, so the numerical aperture of system will be Na1 comma Na2 minimum. Or if we have more number of system, then we can take all values in A1. So from the set of all optical fiber, we'll choose the minimum, and the minimum will be called the numerical aperture of system. I hope this is clear.
Yes.
Yes.
So what you can do, I'll give you some tough question. Just a minute. In fact, very tough question. You can see the question now. So you receive the question. Now
Yes,
most of these questions are the old JE questions, and you can see the old JE questions were really difficult or challenging compared to the present day questions. So you can directly go to the question number 49, which is the bottommost. And try to attempt. And also, I think you have the 41 years of physics. No?
Yes.
Open that first. First, to open that.
Sir, I don't have.
I have given to everyone. Why do you don't have?
So 41.
Yeah, I have given 41 years. Not.
Sir, you sent it last time.
Yeah. Comparison once again. Not an issue.
Sir, which question?
So go to the ray optics chapter and check the question of IIT 2015.
Yes. Is it a passive type
Yeah,
question?
passes. Yeah, passes. You can see the optical fiber.
Yes.
So, which page number is this?
Page number 258.
258.
So from which PDF you have come, sir?
41 years. Huh?
Okay, the second PDF you have sent.
Yeah, I got it. There are many questions. It's a 2009 question. You can see it's again very easy. 2015. Yeah, it's there. Question number, yeah, passage 3. I hope you can see the passage 3. Are you able to see the question?
Yes.
Hmm?
Yes.
So light guidance in an optical fiber.
Sir, what is the page number?
It's page 174 of the PDF. I hope you can see now.
Sir,
174.
174 of the PDF is current electricity.
So please,
174, the page written on PDF. P174. You can see a red box, pink box at the corner.
Yes, sir, got it. Sir, which question?
Passage 3. Read the entire paragraph, then answer, because they might have defined the numerical aperture in different way. Okay, they haven't taken the mu into consideration, only sin I.
So can I show the previous page?
This one.
Yes.
See, you have to go through the two processes. The first step is
Which
check the
question?
boundary at which TIR will take place. Then check the other boundary where the refraction is taking place, and then connect the two through the relation. And of course, you have to use the trigonometry and Snell's law to get the answer. If there is simple rule, the number of refraction is the number of equation. Very simple.
So, passage 3. No?
I have been saying passage 3. No? Should I write here? Passage 3.
So, one PDF just now open.
Let- So how much time you need to solve? Because this is very, very important for you. Once you practice the optical fiber, then only can get, because there are many questions that are based on the same technique, same, almost same. And it is not only for the optical fiber, but for any question in which the TIR will take place. I'll show you some more questions.
So the meaning of cladding is the covering, right?
Yeah. The word clad also means cover.
Sir, I have one question.
Hmm.
Sir, Na is defined for each particular medium.
Hmm. Assuming it is single, like separate, like if you choose only that medium, then what is Na? If you choose that medium, what is Na? And if you combine both, then what is Na?
So here in first option they're asking for water. Then I have to write the nu of water into sin I. That's what they're asking, right?
No, read the. Have you read the paragraph entirely?
Yes.
Read again. It's clearly mentioned.
Sir, I got Na for S1 if it is submerged in water. Then I have
Okay.
to compare it with the compare it to the S2 with which is submerged in liquid.
Yeah,
Right.
you have just it's written there, no? Everything
So
is
like
written there. You have to read the
okay.
option and you have to derive it. And the formula is pretty much straightforward, The sin alpha max is how much? Under root of n1 square minus n2 square by mu1, right? Simple formula.
Sir, I derived it.
Yeah, I mean, of course, you can derive. But this is the simple formula. The sin alpha max is having simple formula n1 square minus n2 square upon. And this is the numerical aperture defined by the question, correct?
Yes.
Sir, I derived the whole formula, but
Yeah,
then
very good.
I'm getting confused in they are asking the numerical aperture of S1 immersed in water is same as S2 immersed in liquid of refractive index 16 by 3 root 15. So, sir, what's the 16 by 3 root 15?
That's the refractive index, no? Something given. Let me read the question. So numerical aperture of S1 immersed in water is you have to prove it. Is same as that of S2 immersed in a liquid of refractive index this. So this is the mu medium. So S2 mu medium of S2 is this. And water
So,
is
can you explain the numerical
no.
aperture again?
This is the numerical aperture by definition.
So then you multiplied that new medium into sine alpha max is equal to numerical aperture, right?
That is what I said. But as per the question is what, that's why I said, no, this depends on the question. I mean, of course, this is the actual what we studied in BTech. But if the IT is saying that take this as numerical aperture, you take that this as numerical aperture. What is the problem? You should not be confused. This is in general. But if I am saying that they take that way as numerical aperture, you take that way. What is the problem?
So first option is correct. For I'm getting correct.
Yeah. And you have to just compare it. This part you can ignore as of now. Imagine that this is not taught to you. No solve. Now you're okay.
Yes, sir.
You have to match each answer one by one. That's it. Then
Sir, what?
Yes, sir. Sir, yes, sir. So option A, C, and option D.
so D is for 17, no? Question number 17. Okay, for this question only, there are three options. Correct.
Yes, sir.
Option A,
C and D.
okay, yeah, have you matched A, C, D? You can check the answer. It's very difficult to check the answer. E174. Question number 6, passage 3. Let me check.
Sir, I got A and C.
I think A and C is the answer.
Yes.
Oh, yeah, sir. Yeah, sir. ANC. So D1, I by mistakenly took
Hmm.
uh, option C is refractive index. So,
Yeah. So ray
Sir,
of
and second one is the 35th state.
that to be discussed already. Yeah. Hmm.
Sir, but why have they given the refractive index of water?
Water is given because when you find the numerical aperture for the S1, it must be with respect to water, na? 4/3 will come.
so the seventh one is option D. It's the second question.
Yeah, that's the smaller one. That's it.
Minimum. Yeah.
The minimum one. Yeah. Hmm. This was the question number 6, no? And what is the like section? Which one? A, B, C, D. Which section is this? The sixth answer is given A in which part? I don't know. Can you check the section? Is it A, B, C, D? The comprehension part?
So it is G.
It's G.
Yes,
Yeah,
sir.
G. For G, answer is A and C. And for seventh, it is D. Is it correct?
Yes, sir.
All right. So this is the optical fiber for you. There are many questions that we can actually create from the same idea. So let's say on a disk, what we have is a paperweight, a transparent paperweight. And anything written here. So something is written here, text, which you can see through the transparent glass. I mean, this cube. It is like a paperweight. So the question is, what is the minimum refractive index required such that no one can read from the side wall what is written there? So whether this observer or this observer, or like maybe, so for text to be not visible through side wall of paper,
So I didn't understand.
wait, find new minimum of Q. Yeah, you're saying something?
Yeah, sir, I didn't understand the diagram.
So the outer so the outer refractive index is here. One.
Yeah, outer is there. It's a table actually. It's a table. And something written here just on the table surface. Okay, so how we
This
think about?
dimension needed.
No, nothing is required. This is a very common question. So the idea is, if this guy want to see the text, the worst case is the light will travel like this. Okay, so how to start solving or thinking about this problem? So we believe that the worst case scenario will be when the light ray is trying to enter almost grazing incidence, almost like this. But this is the worst case, because any light which is trying to go towards the right will have maximum probability to leave the wall and go to the observer. Correct? So, okay, if I draw multiple rays like this, so which ray is most probable to reach the observer on this side? Which one? So what are the chances that the 1, 2, 3 will reach the observer O1?
So one will have the highest probability.
That's common sense. So I'll go with the worst case scenario. Let's say if the ray is trying to enter this particular way. So this I will call the grazing incidence, because this is the medium. So this is how we think about it. So if it is almost grazing incidence 90 degree. So after incidence, it will bend towards the normal, because it is from rarer to denser. It is going from A to the paper weight, and it will go like this. Okay, now we know that if 90 is the angle of incidence, the angle of reflection will be numerically critical, because the light follows the principle of reversibility. So we know that only critical angle refract at a grazing angle or grazing emergence. So the reverse will be also true. Yes or no?
Yes.
See, if the light ray is coming this way at critical angle, it will go like this. So if the light
Yes.
follows the principle of reversibility, if the light ray will come this way, it will go this way.
Yes, sir.
So in both cases, it is going to be critical. I'm not saying it is TIR. I'm saying it is critical in value. Understood? So this is the critical for this pair. And this angle will be how much? 90 minus critical, because the problem is a Q problem. Can we say like this? And for worst case scenario or the best case scenario, the observer O1 should not observe. It means the light ray must reflect back from here, isn't it?
Yes.
So can we say for the given condition, the angle of incidence should be more than critical angle? Can we say?
Sir, why not equal to?
Equal to is also possible. We are taking the inequality, like the minimum value. Anyway, it will come. Okay. So if we make it equal, it will go like this. That's also not an issue. The thing is, the observer should not look through the wall. Okay. So 90 minus theta c should be more than critical angle. Yes or no? Now this is the angle of incidence, right? Luckily, which is also in terms of critical angles. That's why it's easy. Okay. So we are done. So what we can see, that 2 theta c is less than equals to 90 degree. So critical angle is less than equals to. It is only possible when critical is less than 45. What is the value of sine of critical? We can add sine of 45. And sine of critical we know is 1 by
1 by nu.
So mu is more than equals to. And therefore the minimum value that we can expect is root 2. It means if the refractive index is root 2, you won't be able to see the bottom from the side, and that will the side will act as a mirror for you. So you must have observed something like this in a reality. If you have the paperweight, you can understand. You can also do it with glass also. You can take a glass filled with water, and if you see that, okay, through certain angle you won't be able to see the base. Okay, you can do this. Take a glass of water and put a water on a paper and try to see that at what angle it is not visible. Okay. Okay. So now you can solve the question number from that book only. Question number, which question we are looking? Okay. Come to question number. Yeah. So, yeah. Question number 10, page number P166.
Sir, can you read the question because I have the book? So
It's a monochromatic light. Monochromatic light is incident. You don't see the question? No problem. Okay, now you can read question number 10. Okay? So try to read this. Let's do something else now. Okay. So you can practice at home or maybe in the tutorial session. I'll go to the next topic actually.
Sir, so for to solve questions in sheet
Pardon?
and then we have to go for 40 minutes.
Your voice is cracking once again.
We- sir, like first we have to solve the questions from the sheet you sent of that result. Afterwards, you have to share
No, that is like only
spreadsheet
yeah, that is from see if you solve 41 years, na, you will end up solving everything. So for this particular chapter, what I would suggest is that you just finish the all JE problem. That is more than sufficient to practice every question. The 41 year is more than sufficient to understand concept and practice enough questions. And after that, once you're done with this, if you have time, you can solve. Yes.
Yes, sir. Sir, and for rest of the chapters, we have to stick for that sheet.
Your voice is cracking. I'm not able to listen to you. Am I audible?
Yes, sir.
Yeah. Tell me.
Sir, I have solved half of the 41 years from this chapter.
Okay, very good. So finish it and completely because this chapter will have a
no,
lot of questions from
the
subjective also. Yeah.
next topic is prism. That's why I'm not starting.
Yeah. Right. So don't worry. Once we will finish the topic here, you can finish everything. Okay. So let's do the prism now. So what is prism? What is prism? Yeah, for this chapter, you only stick to the J problem. Don't solve anything else. Okay.
So then the prism we have like the two triangular sides and the three rectangular sides.
Yeah. I mean, that's in general, yes. So any that's not the definition actually. So that's why I'm writing any transparent medium bounded by any number of surfaces, not two, just no, three, four, five, infinite. Will act as a prism if
The two
the
consecutive sides should not be parallel.
yeah if the surfaces through which and anyway consecutive sides cannot be parallel.
Opposite sides. Sorry.
Yeah. So again, it's not necessarily opposite. If the surfaces through which light through which refraction taking place are planar and non-parallel. So the whole idea is that we only talk about those surfaces through which refraction is taking place. If those surfaces are plane but non-parallel, we call it prism. So for example, if I draw something like this, let me do something. So how many prism you can see? Let's say this is the cross-sectional view and it is having spread across the into the plane. So you can see there are 1, 2, 3, 4. There are 4 rectangles, right? So again, it is not true that it must have 3 rectangles. It can be 4, 5, 10, and with infinite rectangles. So that logic is again incorrect. Second is they must be parallel. So yeah, parallel. I'm sorry, they must be planar. So yeah, everything is planar. That's fine. And the third is that any two surfaces through which the light will refract, they should be non-parallel. So how many such pair we can create in this case? So we have four surface and we have to pick two. Then we can say 4C2. How much? 4C2 is how much? We have four surface and we have to pick any two which are non-parallel. So 4C2 will give you how much?
6. 6.
And therefore this will represent 6 prism actually. So 1 prism, 2 prism, 3, 4, 5, 6. Understood? So this is not one prism, this is 6. There are 6 possible prism. So prism is not a shape. Prism is the idea that if the refraction is taking place are planar surfaces, but non-parallel, we call it prism. That's the definition. The what is slab? Slab is also the situation when it is planar surfaces are the surfaces through which refraction is taking place, but the planar surfaces are also parallel to each other. So we call it slab. So the only difference from the slab to prism is the parallelism. So one is parallel, other is non-parallel. That's the only difference. And by virtue of the change in such a geometrical arrangement, we need to recalculate the angle of incidence and angle of refraction for both surface. That's the only, you can say, effort. And therefore, the idea of Snell's law will remain same. Only the I and R will change geometrically. That is the only thing. And once you calculate those things, it is again a simple question of refraction. Okay. So we especially talk about something called angle of prism. That's very important. So angle of prism is also called angle of refraction or refracting angle of prism. That's a better way of saying this. Refracting angle of prism. And we are saying refracting angle because only those surfaces are considered through which refraction taking place, and the angle between those two surfaces is called the angle of prism. So it is the angle between surfaces through which refraction so if the light ray will go from these two surfaces, this will be the angle of refraction. So how many angle of refraction we have? How many we have? How many can see? So here the total number of angle of refraction possible is possible are actually what we can say. How many are possible? There are 6 possibilities.
Yes.
Understood. So if I choose these two surface, this is the angle of prism. You can also have angle of prism like this. And of course, apart from this, we have. So these all are angle of prism. So I can call A, B, C, D, E, F. So there are 6 angle of prism: A, B, C, D, E, and F. So it depends on which two surface you consider. Okay. So prism is not a triangle or triangular cross section. Prism can have any cross section. It could be n polygon cross section, n sided polygon also. So it is a concept. It is not a shape. Okay. So prism can come to you in various shapes like this, the way I have drawn. Of course, when we explain certain things in textbook which you have come across, you generally see the triangular cross-sectional view prism, which is generally portrayed in textbook, and that is has led to the confusion that is the prism, that is the way it is shown. The way we need to understand is through the idea that okay, the refraction surface, the surface through which the refraction is taking place, those surfaces should be plane and non-parallel. Okay. So a slab is a potential prism, isn't it? So even if I draw a slab, I can say it's a prism. Why? So let's say this is a prism. So this is a slab. If the light ray will enter like this, and it will go like this, and let's say image like this, the surfaces through which refraction taking place are planar, yes or no? Are planar?
Yes.
Are non-parallel, yes or no? Are non-parallel? So this is a
Yes.
prism, and here the angle of prism is 90 degrees. That's it. So prism is the idea. So a slab is also a potential prism, depending on which two sides you take for the refraction. Is this clear?
Yes.
And see, everything is defined in that way only. So any transparent medium bounded by any number of surfaces, it is not necessarily 3 or 4 or 5. Any transparent medium bounded by any number of surfaces will act as prism if the surfaces through which refraction taking place are planar and non-parallel. If they are planar and parallel, we call it slab. And if at least one of the surface through which refraction taking place is curved, we call it lens. That's the only difference. So a lens is also a prism, a slab is also prism. Everything is prism. So you can think
So
as
sphere is
pardon.
prism with so sphere is a prism
Yeah.
with infinite
Yeah.
angle of
Definitely. It will have the angle from 0 to 180. And you can see that okay, if I put two prism like this way, it will become rectangle. So a slab is also a prism. You can see it's a combination of prism. And if I have a sphere, as you said, I can cut into thin pieces, and each piece will act as a prism. Yes or no?
Yes.
Because it will have the well-defined surface area, and those surface we can treat as parallel surface, sorry, planar surface, and non-parallel. And you can think this way: okay, if you draw a tangent here, and if you draw a tangent here, so this is the angle of prism for this part only. Which part? I can just draw the part. This is this part. So everything is prism. The way to look at it is, of course, will change from situation to situation. Understood? So the idea of prism is clear. What is prism?
Yes.
And in fact, the idea of lens was not there in the very beginning. So we got the idea of prism, and by making the angle change smoothly, we end up creating the lens. And the theory of a lens was actually developed with the help of theory of prism only in the very beginning. And from there, we actually derive all other formulas. Like by understanding the concept of deviation, we got the concept of deviation in lens also. And eventually the prism becomes the lens. I mean, it's a very smooth transition from the two. And the lens was offering you a multiple prism view of the world. You can say that through a lens, I can have infinite prism stacked together. And so at once I can see infinite things, like infinite deviation. And then by designing a particular curvature, we were able to achieve the rays which are focused. Okay, so by deviating the light ray in such a way that after deviation, if all will meet at one point, our job is done. So we are able to focus it. And once you focus, then you can increase the intensity, and then the world will change. Okay, so we can achieve a lot of things. So by carefully designing the curvature, we can achieve various kind of deviation. And deviation is the only truth in the universe. Every optical instrument ever created, whatever you name it, the only thing they can do is they can deviate light. There is no second, you can say, work they are performing. So optical instruments are well designed geometrical shapes, and the purpose of designing such shape is to achieve certain kind of deviation that the light will suffer while crossing it. And through the deviation, we can create certain viewpoints, and that is the whole idea of understanding the optical instrument. So we have defects of vision. So when eye is visually impaired for certain rise, if for certain light, if the eye is not able to bend, we take the help of external bending mechanism. So we wear glasses in front of the eye, and the glasses will bend the light ray in certain way, and the rest you can perform with your eye. So it's like a supporter. I mean, the eventual cause is bend the light, because you're not able to bend the light properly, so you will take help of other. So that's why you wear the glasses. Okay. So deviation is the entire truth of this chapter. The rest is just manipulation. And there is only one thing, I mean, two things in the entire chapter. One is the reflection, other is the refraction, and there is nothing else in this entire ray optics. There is no third phenomenon. And everything we can derive from basic using simply the Snell's law and the law of reflection. We really do not need anything else. So every formula which you have seen so far, you must have observed that I have been deriving that using the Snell's law or the law of reflection. Have I used something else to derive?
No.
Which means we don't have much option, right? We don't have any option. And then the consideration that the ray is paraxial. So for the lens, if the ray is paraxial, then you will end up in a region close to the optical center, which will again give you a definite prism, right? So if you are very close to the, you can say, diameter here, and if I confine the light ray from here to here, I'm in a way kind of confining the types of prism, right? We have only two prism here, one this way, another that way, correct? Again, this is the way of thinking. Just getting absent. Okay. So in prism, what are the things that we need to discuss? So we'll discuss about the angle of incidence, angle of refraction, angle of transmission, or you can say reflection only, angle of emergence actually. So we just need to get acquainted with certain terminologies. Everything is simple. So let me draw a simplified diagram of a prism. So this is a very regular one. Oh, really bad diagram. Anyway. Okay. No, this is better. Okay. So now every surface will have some angle of incidence. So let's see the angle of this is the incident ray. And if this is the incident ray, the first step is, can you draw the normal? Yeah, you can draw the normal. So once you draw the normal, you will talk about something called angle of incidence, right? Everything is like common sense. Yeah, I would do like this is the I angle of incidence. What we will do next? The light ray will refract, right? The next thing it will
Yes.
refract. So it may go the way we see. We really don't want to, I mean, how it will go. Just let's say this will go like this. Okay. So this will be called angle of refraction. Now, the only problem is because the other surface is also tilted, we have to recalculate the angle of incidence for the next refraction. So the next refraction, this is the normal which you can draw, correct? And you can clearly see the angle of incidence, which we generally denote by R dash. And this is again the angle of incidence. And because you're going back to the medium, which is rarer medium compared to the prism, it will again refract away. Correct. And by definition, we call this as E, and the E represents emergence, angle of emergence. So these are like some terminologies. And since I have chosen these two surfaces for refraction, I will call this angle as angle of prism. So for my particular diagram, the angle of prism is A. Now, will it be always true? The answer is no. If I choose these two, my angle of prism will be this angle. Okay. So what the prism is doing? The actual path of the light ray that it is traversing. This is the initial direction of the incident ray. And because the prism came in between the path, now this is the final motion, as you can see. So we are always interested in the fact that how much bending this prism has provided to the light. So while the light was trying to move, you can see from its original path, you have bent it by this way. And this by definition, what we call angle of deviation. So all these things are very much common. You can always relate through geometry. What is R, what is R dash, what is del, what is I, what is E. And we need to learn to express these answers properly. The outer medium, you can assume air, but you can also assume some medium. I'll also assume, let's say mu m. The outer medium is something. So that we can have a very generalized picture of derivation. So the first thing first, if I is given, let's say if I is known to you and E is known to you, can you express the deviation? Can you express the R and R dash? So what are the possible geometrical relationship you can think of? And what are the possible relationship we need to think about? So generally the angle of prism will be known to you in advance. So you will try to relate R with R dash. That's a very common geometrical step you can take. So can you think of the relationship of R dash with A?
Yes, sir.
So what is that? So if this is R, this will be how much?
Sir, it will be the
R
addition.
plus R dash is equal to A.
Very good. So this is 90 minus R. And this is,
Sir, it will be a cycle quadrilateral. So
you can also do simply, it's a 90 minus R dash. And then the sum of the angle of a triangle is 180. So 90 minus R plus A plus 90 minus R dash must be 180. That's easy way to derive, right? So R plus R dash is A. Correct? Also, you can find about the deviation, which is pretty. Just this angle is how much? So the entire is I, this is R, this is I minus R. Correct? And this will be E minus R dash. And in this small triangle, the deviation is nothing but the external angle, which is equal to sum of the far two interior angles. Yes or no? So can we write delta is nothing but the I minus R plus E minus R dash. Tell me yes or no.
Yes, sir.
And now you can see the derivation is a very important concept. It is I plus E minus R plus
We
R
can write
dash.
that as A also.
Correct. So only these two are the important formula in entire prism. The rest is time pass. Okay. Now see here I have taken the condition that the ray is coming out. So we have the angle of emergence, angle of incidence. Uh, so the I is the E is and the R is so R is called the refracting angle. Actually. I mean angle of refraction you can say. So we already defined the angle of refraction for the first incident light. Now there is simple rule. When you solve any question of refraction, there's a rule is simple. How many refraction are you seeing here?
Two.
Two. So you will write 2 times Snell's law. That's it. The very simple thing. So to relate everything, we have to write the Snell's law 2 times. Okay. So what we are trying to achieve here? I mean, it depends. I mean, we have no idea what we are trying to achieve. So this is the like ambiguous question. Like what we are trying to achieve should we clearly mention in the question that this is what I'm trying to achieve, and therefore you can proceed from that assumption to get the desirable answer. Right now we have no goal. It's just like a relationship. That R plus R dash is A and delta is I plus E minus A. So we begin from these two equations. And then if the problem is settlement is given to us, we can solve further. So let's bring some idea or some like end goal, like what we are trying to achieve. So there is one very famous goal that's called condition for. Can you tell me the condition for which the emergence is not possible? The light should not emerge.
All surface should perform total internal reflection.
Not all surface. The TIR is a property when you go from denser to rarer, not vice versa. So tell me in the refraction, which incident is denser to rarer? The first or the second refraction?
So second.
Second.
Yeah. So this is how we think. You cannot, quickly jump to the conclusion. The first ray of incidence will have no question of TIR because possibly it is going from rarer to denser medium, unless we make the everything disturbed and say, oh no, the prism is by default denser. I mean, there is no by default. We can always change the condition, but here, assuming the outer medium is rarer compared to the prism, we can talk about something called condition for no emergence. So no matter what is the angle of incidence, what we can say? The first ray will suffer refraction, isn't it? The only thing that we can expect is second surface. So R dash will decide something, isn't it? And what we don't want? We do not want light to emerge. We want light to reflect back. No emergence condition. So tell me guys, what is the no emergence condition? for no emergence, the R dash must be more than critical.
Yes, sir.
But R dash itself is variable, isn't it? Because we know R plus R dash is A. So R dash will depend on R for sure. And R we can change by changing I. So can we say that in a way I is dictating the R dash? Because I will decide R and so R will decide R dash. So
Yes,
I can
sir.
say that I will decide R dash.
Yes.
And therefore R dash can have some range, some minimum to maximum, right? The question is, this is not a right condition for no emergence. It may be no emergence for that R dash, but I want to know R dash should emerge. What I want? Any value of R dash should not emerge. What does it mean? If I make sure that the minimum is more than critical, can I say anything else will be more than critical?
Yes.
Because if I say the minimum is not coming out, so any other angle will definitely not come out.
Yes.
And R dash will be minimum only when the R is maximum. Correct? And when the R will be maximum, can you guess? R
When
is
I will
only
be
possible when I is max, and I cannot exceed more than 90, right? So for R max implies I must be 90. Yes or no?
Yes.
Because for R max, I must be maximum. And I maximum possible is 90 only, no? Isn't it?
Yes.
Are you getting this entire idea?
Yes.
And we know that if the angle of incidence is 90, for I equals to 90 degree, the R must be called critical angle. If you remember, we have discussed this just some time before. If I is 90, then R will be critical angle because that's the light will follow the principle of reversibility. If the critical angle will let the light go out at 90, so incident 90 will create the angle critical only. Yes or no?
Yes.
See, it's not a big deal. If you're not getting it, you just write the law of refraction, the Snell's law. What do you like?
Sure, understood.
So this 90 equals to mu sine R. So what will end up is sine R equals to mu m by mu, which itself is sine of critical, and therefore I say R is equals to critical. So for I-90, the R is always critical. And now we have all the equation that we need to derive the answer. It's the same process as we did earlier. So R dash minimum is more than critical, which means A minus R max is more than critical. And we know that R max itself is critical, theta C, so we can say A minus theta C is more than critical, since R max is always critical angle numerically. Yes or no? Tell me, guys. Which means twice of angle of critical is less than A. So critical is less than A by 2. So sine of critical is less than sine of A by 2. So mu medium by mu is less than sine A by 2. So mu
So it
by
does
mu
not
medium.
depend on the incident angle.
Yeah, because we have taken the worst case scenario, no? We have taken the worst case scenario, because if that is not coming out, so no one else will come out. Understood? And this gives the final answer. That the mu relative must be more than cosec A by 2. Then nothing will emerge from the prism for sure, no matter whatever is the angle of incidence. If I can achieve this, I will make sure that nothing can come out. Is this clear?
Sir, but the reflected ray can emerge, right?
Yeah, from this surface. See, I'm just trying to make no emergence from this surface. Now I'm not talking about this surface. So this may emerge. Okay.
Yes.
So the context is actually clear. Like that, of course, what you're saying is correct. That it would come out. It may come out from here. But we are not talking about that part. We are saying that generally the refracting surface that we consider, if I'm saying A is the angle of prism, then I'm only considering these two surfaces, and my context is for these two surfaces, not the third or the fourth surface or the fifth surface or the 10th surface. So for these two surfaces, if it is not happening, we can say, what you can say, that there is no emergence. And when we have a diamond, and you see when you go and purchase diamond in future, then diamond will come with multiple cuts. So you will see that, or you can see the ad that it's a 64 cut diamond or 128 cut diamond. So they create so many cuts so that you can have infinite prism actually. And the refractive index of actually the diamond is maximum. It is 2.41 something. So 2.4 Ri is so large that it will have the least critical angle, and therefore the EIR is very easy in case of diamond. So once the light will enter the diamond, it will get trapped in the diamond, and it will just get released from certain surface, and that is why you see sparkling. So diamond will sparkle because it will suddenly from some point it will release the light. So it is like light is coming through one of the corner of the diamond, not from entire surface. So you don't see diffusion. What you see is the leakage of energy or leakage of light. And why diamond is precious? Because of this reason. It is the refractive index which makes the diamond so precious. And of course, it's transparent, not the original one. So the original one is gray in color. You have to rub it slowly to get like transparent. And the size matters. So while rubbing, it breaks down into small pieces. And once it breaks down, the price will decrease. So size matters. So a smaller diamond will have the lesser price. That's why you see that most of the jewelry which is sold in the market, they use the dust particle size diamond, which is like the most broken one, which is of no use, and they put into jewelry by making the tiny pieces of jewelry, and this sell in the market at a very high price, which is actually useless thing in the world of diamond. Okay, anyway. Now using this formula, this is so powerful. This is a really powerful formula. We can go back to this question. We were solving this question, and this is exactly like a prism. You can see this is the prism. Do you realize this? This is a prism, and this is exactly the condition for no emergence. So can we say the mu must be more than cosec A by 2? What is A?
90.
Which is root 2. That's it. So we got the answer directly using the formula, which is actually derivation. So the mu relative is more than cosec A by 2 is the condition for no emergence. So then there are three possibilities. For grazing emergence, the mu by mu medium, we have to make it equal. If it is equal, it will emerge at the grazing angle. And for proper emergence, this is less than this value. That's simple. So all conditions we can derive once we know the. And therefore, when you solve a question of prism, you cannot take it granted that it will go on the other side. So you have to check that condition, that is the mu by mu m ratio and the cosec a by 2 ratio. You have to check which one is true. So based on the relation, you will further decide the light ray. So any question, if you're solving for the prism, you cannot take it granted it will go on the other side. So first you will take the reflection only at the first surface. You will check the condition on the other surface and then you will solve. Is this clear? So please do not assume that light will always emerge from the prism. And JEE will ask question like that. Always. So let's say when not to apply this formula. If the light ray is itself enter at right angle, if it will enter at right angle, then can we say there is a refraction at first surface?
No.
No, there is no refraction. And because there is no refraction, we cannot apply any of the prism formula. A prism formula is a formula which we obtain through two refraction. And if it is not, we will never say it as refraction. And TIR is also taken as a one special case of refraction. But here we don't have refraction, we have only right angle. So this is 90 degree. So what is this angle of incidence? So this is also A. Can you see that? This is always A.
Oh, yes.
This is 90 when I say. And because the angle of incidence is A, then if you want to check whether the emergence will take place or not, you have to re-derive the formula. So for no emergence here, what we have to write? For no emergence, the A must be more than critical. Understood?
Yes.
So the critical is less than A, so we can say sign of critical. And why this was important to be revealed? Because you might have used this formula which will give you wrong answer. Now this formula we derive under the assumption of two refraction. And here we don't have two refraction. So actually the whole idea of prism is gone here. So it is like deceptive prism. So the entire geometrical shape has nothing to do with the prism concept. Understood?
Yes.
Although it looks like a prism. So you have to understand through the concept of ray, concept of refraction. The shape is not the way to use the formula. These kind of things are very, very crucial if you want to master this ray optics. That when to apply, when not to apply, what to apply. So here things are simple. You simply derive it. Your life is sorted. And now this is the answer. So for no emergence, have I written? Oh, I made a mistake. So this is mu medium by mu. Is less than sine A. So mu by mu medium will be more than cosec A. Okay. So this is the now this is the condition. And you can see there is a clear distinction. These two formula are not same. So earlier the condition for no emergence was mu by mu medium is more than cosec A by 2. But now it is only cosec A. Understood? And why it is happening? Because the earlier
Correct.
formula that we derived, we cannot apply here because here there is no refraction from the first surface. Is this clear? Yeah, you were saying something?
Sir, equality will also change.
No, no emergence means not equality because this is called grazing. This is called grazing emergence. It is emergence actually. Understood? So you can say for grazing emergence, is this clear? Understood?
Yes.
So you can say for emergence, what you can write? So again, you have to be careful. So this light trick is given to you like this. Then after that, it is quite possible it may go like this also. Like this, like this. Understood? So whether it will go this way or this way depends on whether A has exceeded the critical angle or not. So you have to always check. So you have to be very careful. The moment light is suffering a refraction, but is going from the denser to rare, you must be, this is like a checkpoint. First, you will check the condition, then only you will do the next step process. So you will never jump to the conclusion. Okay. You have to stop and check. It is clear? Hello, guys.
Seriously.
It is clear or doubt?
No, sir. Clear.
Okay. Now, after this condition, the next concept that you will come across is condition for a minimum deviation. Now, you may be wondering why this condition is at all required. So condition for minimum deviation is actually a method. It's an experimental method to determine the refractive index of a prism. So let's say if I'm a manufacturer basically, and I'm manufacturing multiple prism. So I have got some material. Let's say I went to some the mineral site or the ore site, and we extracted some transparent object, and we simply made the prism. So this technique is helpful in determining the refractive index of that medium. So to understand that refractive index of the transparent material, we generally cut in the shape of a prism. So that is the first step. We cut into shape of a prism. And once we cut that into shape, the process of determining is fairly simple. And we'll see why it is simple. So it comes through the various logic.
Sir,
Yeah.
can zero deviation be possible?
Zero deviation for this case is not possible. So even for this case, no matter how the light will bend for sure. So is it possible for light to go like this? No. It will go like this or like this or like this or like this. So deviation is bound to happen. Correct. In the previous case, we have for sure deviation. But in a special scenario, we can create a zero deviation. Now, what is the special case? So for single prism, we cannot achieve it. So to achieve the zero deviation, we bring the combination of prism. And through the combination, we achieve the zero deviation, which is the again our topic of interest. So we need a different pair of medium. So if this pair is trying to bend towards normal, I need a pair which can do the reverse process. And therefore, by bringing two prism or more than two prism, we can achieve zero deviation. So those things are there in our syllabus. We will study.
Okay, sure.
So for any regular isosceles prism, the angle of deviation, and if you plot the angle of incidence, you will get a variety of answer. And if you plot the graph of the angle of deviation versus angle of incidence, the graph will come something like this. And looking at the graph, you can see that every deviation angle will occur for two values of I. If this is some deviation, so the same deviation we will obtain when I is I1. So every deviation will occur for two values of I. And that will be evident from the formula that a deviation is how much? Now from the principle of reversibility of light, if I make I as E, the E will automatically become I, and it will end up giving you the same answer. So I and E are a pair of angle which will give you same deviation. Now here E is the value of I actually. If the angle of incidence is same as the, let's say if the angle of incidence is 30 degree, okay, and you get the angle of emergence as, let's say 40 degree. Imagine the situation, you have I30 and you get E40. If I will make the I as 40, I'm going to get the E as 30 again. Therefore, the 30 and 40 are the angles at which you will end up getting the same deviation. But when the angle is, when the deviation is minimum, you can see this is the lowest possible deviation. And minimum deviation will happen when we have the unique value of I, which means it is only possible when I and E becomes equal, because now we don't have two options, we have only one option. So minimum deviation occurs when the angle of incidence and angle of emergence becomes equal. Then you get the minimum deviation. That is the whole idea about this. And of course, it is derived mathematically. And of course, you can derive it using the rigorous differentiation and maxima and minima concept. So those rigorous calculations I will leave up to you. That I will show you how to do this. but I'm not going to derive it. It's a lengthy differentiation. Okay. So now the deviation, which is in general I plus E minus A, but the minimum deviation is a very simple answer. What is the minimum deviation? It is either 2I minus A or 2E minus A, because I and E are same. Understood? And experimentally, we perform this on a turntable. So we have the collimator, a laser. You can choose a laser. So you can see this experiment. So on a table, a prism is kept. A source of light will enter. Okay, sorry. So the the direction of light ray, and there is a collimator tube, which means this is a small tube through which you can see the light. So the source of light is also fixed. It is generally a laser, of course, less powerful laser. And so for if the light ray is going this way, it will not reach the collimator. So you won't be able to see the light. So you will keep on turning the table till you see the light again. And the moment you see the light, you know that the minimum deviation has occurred, because these are placed symmetrically. I mean, of course, you keep on moving the collimator or you turn the table, and we keep on changing this angle. So this is like slide. You can slide it. You can slide like this. I will show you this. Maybe on Google it is available. Just a minute. Let me check. I hope you can see this now.
Yes, sir.
Yeah. So you can see there are many things. We have eyepiece. We have prism table. We have collimator through which the light ray will come. And the turntable, the leveling screw prism table. Okay, this is prism table, we call it. We keep on turning till we receive the light. So they are placed in such a way that you can see this is turning. You can see this part. So you can see this part is able to turn, right? This is fixed part. So this is like a fix with this, and you keep on turning this way. So you keep on turning till you get the light ray visible. Okay. And once it is happening, the angle can be seen on the table. It's a calibrated table. You can see the angle. And it is so accurate that you can see the 1/100th or 1/10th of a degree. It is accurate up to that level. So of course you can find the refractive index up to third or fourth decimal place. That is the whole idea, to find the more accurate answers. Because these are important from the you can say commercial point of view, because they have to rate the diamond price, and for pricing of diamond it goes to the fourth place of decimal. So if the answer is, if the value of mu is differing in the fourth place, the price will change. So these are very expensive, expensive device. But in lab, in school lab, we use the cheaper one, because of course we are not going to sell diamond, right? If a diamond merchant, you will have all those devices to achieve the. And there are many other devices actually to find the refractive index of other gems or diamonds. Anyway, so at minimum deviation condition, the I becomes equals to E, and therefore only one answer we get. You can see the at a minimum deviation, we have only one answer. And the symmetricity will prevail, which means if I equals to E, then can we say R must be equals to R dash? Can we say?
Yes, sir.
And we know that R plus R dash is how much? A. So in that case, the 2R becomes A. So R equals to R dash also becomes A by 2. So the minimum deviation condition is very interesting. So this we can determine experimentally. And the I value we can express in terms of minimum deviation. So I we can attach A plus delta minimum by 2. It is not I plus del by 2, it's I plus delta minimum by 2. So we know the I value through experimental value of delta minimum. So given the del minimum, we can find I. And for that condition, the minimum deviation condition, R is always A by 2. And because we know I and we know R, the Snell's law will give me the refractive index of the prism. And since I am deriving it in general, so using the Snell's law, what we can write? The mu medium sin I must be equal to mu sin R, correct? So mu by mu medium is how much? Sin I by sin R. It is okay. Now this is always true, but for minimum deviation, this will have very nice way of writing. We can write I as A plus delta minimum by 2, and R you can write as A by 2. And because generally A and delta minimum is known to us, so A is a geometrical property which we know anyway, and delta minimum we can derive through the experiment. Knowing these two answers will lead to the ratio, the mu relative. And if I make this if I do this experiment in air, I can get the exact refractive index of the prism. And the idea is not prism, idea is the material, because once we derive, we know this is the this material will have this much refractive index. Understood? Hello, hello, hello.
Yes, sir. Yes, sir.
So are you realizing that why these things are important? These things are actually important from the point of view of gemology. So if you want to pursue gemology, because India is a very good, you can say, manufacturer of diamond or gem-based jewelry. Of course, we don't have the sufficient ore to extract all these expensive minerals, but the entire world, they are not very craftful in terms of creating those nice cut and jewelry. So even Africa is the maximum, the biggest producer of diamond. For all the servicing, you can say, the cutting part and shining part, it comes from India only. And then here in most of the Gujarat states are doing it, and we have many diamond merchants in Gujarat. Anyway, I hope you know this fact. Okay. So this minimum deviation is a very, very important formula for you, and we are going to use this to derive something more. Okay. So one particular interest that we have right now is called thin prism.
Sir,
Yeah. Tell me.
so can you leave the class by 1:45?
Or you have some other lecture?
Sir, yes, offline chemistry and math.
Ah,
Yes, so it is by 2:30.
then you can leave now. We can start the thin prism next lecture. Not an issue. Okay.
Okay, sir.
All.